In this lecture video, we're going to be looking at the sampling distribution of the sample variance. In particular, we're going to be interested in determining the mean of the sampling distribution of the sample variance. So let x1, x2, and so forth up to x sub n be a simple random sample of size little n from a finite population of size capital N, with population mean given by mu and population variance denoted by sigma squared. Let s squared denote the sample variance, the version with n minus 1 in the denominator. All right, so this is the usual sample variance that we're used to now. And notice here that in the formula for the sample variance, instead of denoting the sample mean by x bar, I'm denoting it by mu hat. You'll recall that this is the notation that we're using for an estimator, and in particular an unbiased estimator of the population mean. All right, but don't worry about that. This is the same formula, the same expression that we've used in the past. All right, so this is the statistic, the sample variance that we're interested in, and what we're wanting to do is learn something about the sampling distribution or probability distribution for this statistic. Now, let's denote the mean of the sampling distribution by mu sub s squared. All right, so this is the expected value of s squared, or the mean of the sampling distribution of s squared. And it turns out that when we are using simple random sampling, the mean of the sampling distribution of the sample variance, in other words, the expected value of s squared, is equal to capital N, the population size, over capital N minus 1 times sigma squared, which is the variance of the underlying population. All right, so let's consider an example. We're going to be again using this population, this finite population of 6 values. And so what we want to do is to construct the sampling distribution of the sample variance for simple random samples of size little n equal to 2. And we want to use that to determine, for this situation, what is the mean of the sampling distribution of the sample variance. In other words, what is the expected value of s squared? So to do this, we're going to use the same approach that we used in previous examples, where we were looking at the sampling distribution of the sample mean. In this case, we're looking at the sampling distribution of the sample variance, but the same approach and technique can be used. And so with that in mind, I have another template here containing all 30 samples of size, simple random samples of size little n equal to 2. And I have a column here for the sample variance, s squared. And so what you need to do, what I want you to do, is to calculate the sample variance using, well, here's one formula. I'll show you a simplified formula for the case where you have samples of size 2. All right, and enter those into this column. And then once you've done that, then we're going to add those up, calculate the sum, and then we'll divide that sum by 30 to get the mean of the sampling distribution of the sample variance. Now, when we are dealing with samples of size 2, this formula here for the sample variance simplifies to something that's going to be a little bit easier to use, especially since we have to calculate the sample variance for 30 samples. And so it turns out that the sample variance, which again is defined using this formula, here's the computational formula, but for samples of size 2, it's even easier. Right? For samples of size 2, the sample variance can be calculated in this way. So what we do is we take the difference between the two sample values, square that difference, and then divide that squared difference by 2. Okay, so when we do that, then we get these values for the sample variance for all 30 samples. And so you can see those values there. And but go ahead and do this exercise yourself just to make sure that you get the same values. Then we calculate the sum and the mean of this column of values, and we get a value for the mean, the population mean of, or the mean of this population of values, the sampling distribution values, is 114.7. Okay, and so that is the mean of the sampling distribution of the sample variance for simple random samples of size little n equal to 2 taken from this finite population of 6 values. Now, from our empirical calculations that we just did, all right, which are the results of which are shown down here, all right, the mean of the sampling distribution of the sample variance for this situation. From our empirical calculations, we have determined for this example that the mean of the sampling distribution of S squared is 114.7. Now, what does the theory tell us it should be? Well, according to the theory, the mean of the sampling distribution of S squared is equal to cap n minus, or over cap n minus 1 times sigma squared, which is the variance of the underlying population. Now, n is 6, cap n minus 1 is 5, and so according to the theory, 6 over 5 times the population variance, which we can use this representation for the population variance, 1147 over 12, all right, and so we can see here that that is equal to 114.7, and that matches what we get empirically, all right, and so we see here that the theory is absolutely correct. And again, this is not a proof of this result in general, it's just a demonstration that the theory holds in this particular example. Now, recall that when sampling from an infinite population or from a finite population with replacement, in other words, when performing or utilizing IID random samples, that the sample variance is an unbiased estimator of the population variance. In fact, let me scroll back here to the slide with the formula. You'll recall that the reason that we divide by n minus 1 in the sample variance formula under IID random sampling is to obtain an estimator that is unbiased for the population variance. All right? So that's the whole reason that we divided by n minus 1 in the first place. Okay, and so that's what we're saying here. The sample variance, because we're dividing that in that formula, dividing by n minus 1 under IID random sampling, that makes that sample variance an unbiased estimator of the population variance. Now, this last result implies, however, that when sampling without replacement from a finite population, the sample variance is not an unbiased estimator of the population variance, but rather tends to overestimate the population variance. Now, why are we saying that? Well, again, we've shown here, both empirically and then using the formula given by the theory, that the mean of the sampling distribution of the sample variance in this situation is 114.7. But now, what was the variance of the underlying population? The variance of the underlying population is 95.583. All right, so we see that the mean of the sampling distribution of the sample variance is larger than the variance of the population. And so that's what we're saying here. In this particular example, the sample variance is not unbiased as an estimator of the population variance, but it's larger than the population variance. And in general, it will, under simple random sampling, the sample variance will tend to overestimate the population variance. Now, the amount of bias that S squared has as an estimator of sigma squared is given by this expression here. All right, and so this is, we read this as the bias of S squared, the sample variance, as an estimator of sigma squared. And the amount of bias is equal to sigma squared, which is the population variance, over cap n minus 1. Now, both the numerator and the denominator are positive values, and so what this tells us is that the bias of the usual sample variance as an estimator of sigma squared will always be positive. All right, the bias is larger for larger values of a population variance, and it decreases, attenuates towards 0 as the population size gets larger, or for larger population sizes. And that's what we're saying here. So for a fixed population, a population with a given population size, the sample variance, S squared, will be biased as an estimator of sigma squared, and it will tend to overestimate that population variance. Now, From our empirical calculations, we can actually, we can do two things here. We can use our empirical calculations to calculate the amount of bias that S squared has as an estimator of sigma squared in this particular situation, and then we can compare that to what the theory says it should be. Now, the bias of S squared, the sample variance, as an estimator of sigma squared is equal to the expected value of S squared, in other words, the mean of the sampling distribution of S squared, minus the population variance. All right, and we know both of those now. We know that the mean of the sampling distribution of S squared is 114.7. We also know that the population variance is 95.583. The difference is 19.116. Repeating, if we were to round that to 3 decimal places, it would be 19.117, obviously. We can also express this as 19 and 7/60ths. Okay, what does the theory tell us that the bias should be? Well, according to the theory, the bias of S squared as an estimator of sigma squared is equal to the population variance divided by cap n minus 1, the size of the population minus 1, 1147 over 12 over 5, right? That's 1147 over 60, which again is 19.116 repeating, or 19.117. So we see that we get the exact same value, right? The value of the bias of S squared as an estimator of sigma squared that were given by the theory is exactly equal to what we obtained empirically for this example. So again, going back to slide 16, we see the formula given by the theory for the mean of the sampling distribution of the sample variance. We see here that it's actually, we can tell by the formula that this is going to be larger than the population variances. So right here we could see that S squared, under simple random sampling, the usual sample variance is not going to be an unbiased estimator of the population variance because its expected value, in other words, the mean of its sampling distribution, is not equal to sigma squared, but something larger than sigma squared. In addition, we see here the bias, a formula for the bias of S squared as an estimator of sigma squared that is given to us by the theory. These are both very good formulas that you need to have in your note sheet. All right, and so now we've learned some useful things about the sampling distribution of the sample variance under simple random sampling. And we can use this information to come up with estimators that are unbiased for the parameters that we're interested in particular. And we've already seen that the sample mean is, in fact, an unbiased estimator of the population mean. And we can use this information, let me scroll back to it here, we can use the information on this slide, slide 16, to come up with an unbiased estimator of the population variance under simple random sampling. We'll do that in the next lecture video.